Okay, let's get started. So this is 304. Welcome to the jungle. Um, you probably have heard a lot about this class, but it's a really awesome class, and I hope you like it as much as I do. So I'm Ryan Dougherty. You can just call me Ryan, um, or Professor Emperor Your Highness Dougherty. That also works too. Extra bonus points. My office hours are in 303 on Mondays between my two classes and after this one. I'm actually not sure if I'm holding office hours next week because I don't have the key to my office yet. So if I don't have the keys to my office, I'll just hold office hours right outside my office. So it's in that area over there, and it's right out. I'll just hold it right outside. So there is a textbook for the class, which is Intro to Theory of Computation by Sipser. This is one of the most well-known textbooks in this for this type of class. It is absolutely not required, but for the main reason that it's really, really expensive. And in fact, I'm gonna follow the textbook closely anyway. And there are some things in the textbook we're not gonna cover at all, so I don't want you to be confused. There's enough to be confused about in this class anyway, so I don't want you to be additionally confused. I gotta update this. Lectures are in here, obviously. Labs are on Wednesdays. We do have lab today. So we will meet in, I guess, here later today. And that lab will be purely just review type stuff because we didn't have class Monday and we don't have enough time to get to real stuff today. Any questions about contact info, all that stuff? Okay. Yeah, so here's the course description. I'm going to talk more about that when we start the actual material. Some major topics, mainly the things that we're going to probably cover throughout the semester, or I hope to get to. So here are some course pages. So we're going to host everything on Slack because I don't like using Moodle, and you probably don't either. So the link is right here. If you don't have the invite link already, just use this link. If you don't, still can't make this link work, just let me know and I can give you access. So the syllabus is already posted there. All of the assignments will be posted. Everything will be posted there. I have been affiliated with this class for a long time, and there's plenty of resources for help for you. So I've taught this class 3 times already in my former university and done a bunch of lecture help things. So in 2017, I did these things called recitations, which are basically lecture help. And so I made a gigantic playlist of all the lecture help sessions I did then. Then when I taught it, I have a playlist there of all the lectures I've ever done. And in fact, I'm going to do the same this semester. 2018, I did the same when I taught it. 2019, I did the same when I taught it again. So I've already posted the playlist link in Slack for the YouTube playlist. So if you don't understand something immediately from class, which is going to be a lot of the time, I'm letting you know, then you have the opportunity to go through lectures again. So if you happen to miss a class or whatever, you can just look at the video and everything will be good. Any questions about any of that? Okay, so some assessment type things. There will be some homework assignments, 10 of them. There will be a quiz every lecture, not today. There won't be one today because we haven't talked about anything yet. So those will work in the sense that I will give you a piece of paper with the quiz, quote unquote, on it. You complete it and then return it at the start of the next class. And then you'll get another one, turn in the next one. And so it's basically just a few short questions about, did you understand the thing that we just did? And if you understand that, then you can actually start keeping up. Because one of the problems that I've seen over and over with students in this type of class is that they fall behind really, really quickly. because the material builds upon itself as it goes along. It's not like midterm 1 done, now I can erase my brain, now I can focus on the next bit. It doesn't work like that. It's all cumulative in some sense. Then we'll have 2 tests in the middle of the semester, and then 1 final exam. And my policy with exams is that if you do better on the final exam percentage-wise, it replaces earlier worse, quote-unquote, midterms. So if you got like a 90 on the final exam and less on the other 2 tests, it just replaces them. Because it makes sense that if you show that you understand the material at the end, there's no reason to penalize you earlier on because you show that you understand it. Any questions on assessment type things? Okay, so some appeals. If you feel like you've been unfairly graded for whatever reason, just follow this policy and then you'll be all good. Late homework, please don't turn in homework late. But if you, for whatever reason, turn in homework late, then there will be a 30% penalty per day, and then it just keeps going down. So make sure to turn in assignments on time. Things happen in the semester, as you know, so yeah, so just consult the administrative dean and let me know if there are any accommodations I need to actually make. Let's see, so we have a lab this semester, so once a week we meet in labs, as you know. These are just some basic things about like lab protocol, yeah, all that kind of thing. In labs, we're going to be working with pairs. So not the fruit, but like in pairs. So you'll pair up with someone else and then you'll complete the lab together. By collaboration, I mean you can work with the person, obviously, who is your partner, but I don't want you to solicit solutions outside of your group. You can ask for help in terms of understanding how a question is phrased or things like that, but not like get actual solutions from other people. Yeah, so academic integrity, we'll address that in a bit. Lab grading, 30% attendance, 70% of the weighting is for assignments, and that's basically just for completion. If you complete it in a satisfactory way, then you'll get the full points. So it's not like it's I'm not going to grade harshly or anything. It's just, do you understand the material enough to make it satisfactory completion? Any questions about labs? I'm going kind of quick because we missed a day, obviously. Okay, so this class, in my experience, I don't know if it's the case here, is the most difficult class for some people. So we have 2 TAs who are going to be assisting us in the lab, so you can get help from them. There are open lab hours, so I would check to make sure when those actually are. If you have any disability accommodations that need to be made, please let me know as soon as possible, and I'm happy to make arrangements. And then just some other things about like, if you need help with your machine, or if you need some counseling, or help with your writing, all that kind of thing. And I put the links to and the phone numbers to all the resources in there. Okay, the number 1 section I hate talking about, but I absolutely have to every single time. Because every single time I've taught this class, there's been an academic integrity violation. Okay? The reason it's 31 is mainly because of the times I taught this class. So what is okay? What is okay is telling people about the class, whether what you learned, what you like about the material, what you don't like about the material, and that sort of thing. What is not okay is saying, please give me your solution to X problem. Okay, send me your solution and then that's what I'll turn in. You're absolutely okay to use any source that you want. It doesn't matter, you can use any source online, you can use any person in the class, you can use any source you want as long as it's written in your own words and you cite all your sources. There's no penalty for citing your sources. So if you use any resource at all, please cite it and then there's no penalty for that. But it has to be written in your own words. Okay, is that clear? Anything that I can make clearer? Because I'm telling you, this class is hard. It's difficult. I'm not going to sugarcoat it. So students are more tempted to resort to this type of action. So I obviously don't want that to happen. So please seek help if you need it. I'm always available in my office or by email or on Slack. The TAs are available during labs. There's open hours for CS students available. There's plenty of resources available, and all the lectures that I posted already. So there's plenty of resources available to help you. Okay. Okay, any questions about integrity type things? Okay, so here's a tentative schedule. Of course, this is probably going to change, but this is what we have for now. And I'll let you know if there are any updates to it. Okay, any questions about syllabus type things? Yeah.
Can you explain like the book? Like, do we need, like, I guess you said like you don't need the book. What is it? Can you explain that?
So the things that you don't actually need anything from the book in the sense that the PDFs that I'm going to make here are going to be completely sufficient. I'm going to follow the examples and the concepts in the book pretty closely, almost verbatim. So it basically, I'm going to reenact what the book has, but it's not like I'm going to be assigning, complete problem 1.31 from chapter 1 or something. If I want to actually do something like that, I'll give you the entire text of the problem. So you don't actually need anything from the book. It's just that if you feel like my lectures aren't sufficient enough, then there's a resource available to you, which is the book itself. It's just that I don't recommend getting it because it's so expensive. And I'm sure you know other ways of actually obtaining books, okay? So, yeah. But, so you don't actually require the book for this. Any other questions? Okay, so let's actually get into real stuff. Okay, so let's talk about theory of computing. So let me ask you a question that has exactly one way of looking at the question. There's only one correct answer, and it's completely unambiguous what I mean by this question. You can tell that I'm joking. So here's the question. What's a computer? I mean, you're juniors. You probably should know what a computer is by now, right? What's a computer? Yeah.
I assume it's a box. It's like a piece of metal that does calculations in one and zeros.
That seems reasonable. Any other guess? Let's travel back 80 years. What was a computer then? Yeah.
It was like an actual person. It was the person that's using like typewriters and stuff.
Exactly. So a computer way back when was literally an employed person who did calculations him or herself, who had these stacks of papers and was writing down calculations on the piece of paper physically. It wasn't an actual machine, like working with binary or whatever. So, but let's think of more of a computer nowadays, let's just say. So if we want to look at a computer nowadays, what is absolutely needed for a computer? So if I'm looking at this laptop or this iPad right now, what things do I actually need to carry out the functions that it has? Yeah.
Power?
Power, yeah, that might be possible. But it's just that some computers don't actually need power. They can be completely mechanical. So it's not necessarily power, but it's related to that. Yeah. It's some kind of input, yeah. Because if there's no input, how do you actually compute something? Right? So we need some type of inputs. And of course, there could be more than one. So, for example, there could be keyboard input or mouse input or sound input or file input or a bunch of possible inputs for sure. And if there are inputs, what do you think there are also? Yeah, outputs, exactly. And I put these arrows here for a reason. So outputs could be a picture shown on a screen, or a sound that plays, or something is written to a USB device, or some type of output happens. But what happens in the middle? So how do we get from inputs and convert them into outputs? What has to happen?
Some kind of operation.
Some kind of operation, exactly. So I'm going to rephrase that, but you have the right idea, which is computation. And by the way, I'll make all these PDFs available to you and whatnot. So, yeah. So that's what a computer has. Does a computer need anything else? I don't think so. Because every single thing that we do on our computer involves either putting input in, doing computation, or presenting output of some kind. Maybe different kinds of output, different kinds of input, different kinds of computation, but it's always one of those three categories. I'm going to do something that may seem a little strange, which is going to happen a lot this semester. So I said inputs here. Would it be okay if I scratched the S off and just say there's only one input? But there could be keyboard and mouse and sound and USB device. All of those could be inputs at the same time. So am I justified in saying that I can just say that there's only one input? Why? So here's why. So why am I justified in saying that? So a lot of the things that we'll be addressing in this class is we'll look at a concept like that and then try to understand why it's true. Not just that it's true, but it's more important why that it's true. So why can I say that we can assume that there's only one input? Let's just say that there are 4 inputs. So let's just say there's input 1 right here, input 2 right here, input 3 here, input 4 here. And in order to work with these, what is the simplest way of representing what the input might look like? So if I read the input off a USB device, what things am I reading? Yeah, I'm just reading bits. So all 4 of these inputs are just a stream of bits. So if I read input 1, I may see an input like this. And then input 2, I might see a different set of bits, but again, some kind of input. Same with 3. And maybe let's just say that one, let's just assume that they're all the same length. And then I'm just making all these up. So we could have 4 completely separate inputs. Is there a way that I can put all 4 of these together into one input stream?
Just do it like I1 plus I2. Just so that it's one.
Oh, you mean concatenation?
Yeah.
Yeah, so that's one way you can do it. So you can just string them together. Another way you can do it is to cycle through the inputs. So what you can do is say, let's look at the first bit of the first input, and I'm going to put that first. So this is going to be the one input conversion. So I'm converting 4 inputs into 1. And then I'm going to look at the first bit of the second input and put it second in the resulting input. So basically, what we're doing here is we're just cycling through the 4 inputs and then just concatenating them together. And then let's do pink for this one. And then once I do those 4, then we go through the second inputs for all of them. So from this one input that we have made, can I reconstruct the original 4 inputs? From the one, can I yeah, I can, because if I wanted to reconstruct the first one, I just look at the first bit, the 5th bit, the 9th bit, and just jump 4 at a time. If I wanted to reconstruct the second one, I just look at the 2nd, the 6th, the 10th, etc. And the same thing for the 3rd input and the 4th input. Okay? So without loss of generality, we can assume that there's only one input. Pretty cool. What about the output? Can we do kind of the same trick? If there are multiple types of outputs, could I just amalgamate them into one input, one output, just like we did with the inputs? Yeah, I think we can. So I can also assume that there's only one output. One output string of characters, of bits. Any questions about that? I'm going to actually do something even more drastic. I'm going to eliminate output completely. Actually, I'm going to leave it there, cross it off. And instead, what I'm going to do is I'm going to say the output, quote unquote, is going to be 0 or 1 and nothing else. Now, that surely has to be a big restriction there. Or is it? Am I justified in doing that? In fact, I am. Here's why. So, if we look at a program, what does it actually do? What does a program actually do? Well, it takes some input string and outputs a string. So how can we think of a program? We can think of it as a function from strings to strings. So a program is literally just a function from strings to strings. Interesting. So what could we do here? Well, here's what we can do. For the output, if a string is possible to be outputted, attach a 1 to it. Otherwise, attach a 0. Okay, well, what are we really doing here? We're basically just saying, instead of outputting the actual string, we're outputting an indicator as to whether or not that string is desired or accepted. So, for example, so if we look at the function let's say that it takes an input x and outputs the next prime number oops, number after x. So if I give you 6, what should the next prime be after 6? 7, right. So is 6 possible to be outputted by this function? No, because 6 is not prime. So for 6, oh, sorry, not input. For output 6, we're going to attach 0 to it. And for output 7, we're going to attach a 1 to it. So all we're really doing is reducing the output space to just 2 values, either 0 or 1. 1 being that the result was obtained, and 0 if it's not possible to obtain it. Okay, so in fact, our model for our computation then is actually really, really simple, which is that we have exactly 1 input, we have some computation that happens, and there's only 1 bit of output, which is either 0 or 1. Any questions on that? Okay, so what can we do with this then? Well, let's actually talk about that computation piece, because I think we have nailed down the input and the output parts. Let's talk about the computation part. So let's talk about computation. So think of a computer. You probably think of computers all the time. Think of a computer. If I save the state of this machine exactly as it is, and turn it off, and then turn it back on in the exact same configuration, will it do the exact same thing? So if I take a program that's currently running, and I stop it at some point, I go get a coffee, I come back, I restart it, would it do exactly the same thing every single time? What would be the issue?
Wait, so are you actually restarting the computer, like wiping RAM, or are you just pausing that thing?
It won't matter because I'm restoring the memory as it exactly is. The configuration's identical. And suppose that it's not connected to the internet or anything. It's just the machine by itself. You better believe it. Computers are deterministic. Okay? So, unless there's, I won't go into that. We're going to say that computers are deterministic. So, we're going to focus on, for at least now, deterministic computation. So deterministic, of course, means same behavior each time the same computation is run. So, like for that function we had earlier, if I input 6, the answer will always be 7. No matter when I run it, it'll do the exact same thing every single time. But let's actually talk about what happens in the middle. So when we get this input, then obviously some steps have to be done before we get to the output. It's not just a giant black box where we just feed something in and something comes out. There's steps that happen along the way. So what happens in your computer? So like when the program is running, then there's some the memory is laid out a certain way. Then an instruction happens. Then the memory contents either change or they don't. But something happens. So what can we think about this? Well, we can think of this as saying that each instruction is a function from memory space, whatever that means, to itself. And by memory space, I mean the space of all possible memory configurations. So if I have 10 bits of memory, then each one of those bits could be 0 or 1. So I have 2 to the 10 possible configurations of that memory. And when I execute an instruction, then it's going to either make the contents exactly the same or change them in some way. So we can think of each instruction then as just a function from memory space to, again, memory space. So some memory configuration, then output of that is a potentially different memory configuration. Any questions on that? Okay. But also, never mind. So what we're going to do then is for each memory config, we will call this a state of the machine. And by the way, if my handwriting is atrocious, please let me know. Sometimes I can't even read my own handwriting, but it's another story. Okay, so for each memory configuration, we're going to call that as one state of the machine. So each instruction then is going from a state to another state of the machine. But at some point, the computation stops. So we do instructions for a little while, and then at some point, the program's going to say, I'm done. I'm not going to read any more of the input. I'm not going to do any more computation. So at that point, we need to attach to each state an indicator of whether the state should be a 1 or a 0. So remember before we reduced the output space to either 0 or 1, and now for each state we're going to attach to the state whether or not it's a 1 or a 0 state. And we'll talk about what that means in a bit. And we'll formalize all of this. But any questions about this? Okay, so let's actually make a really simple machine. So I'm going to draw what the machine is, and then I'll explain everything about it. So here's the machine. And that's the entire machine. So you may have some questions about this. Yeah. What is that? Well, I joke sometimes that people walking by look at some of the things we're going to do and they think that we're talking in some alien foreign language, right? So yeah, so what is this? So the circles here are states of the machine. So in Q0, Q1, those are the names of the states.
What's Q?
Oh, it's not a, yeah. You see how my writing can be atrocious? So yeah, it should be a Q. Yeah, I'll try to make it clearer. Maybe I can change the pencil size. Okay, so yeah, so the circles here are the states of the machine. So this may seem like a really simple question, but how many states are there in this machine? 2. You may have a question why there's a double circle on one, but we'll get to that. So there are 2 states of this machine. So yeah, so let me write in the font. So 2 states. Okay. So what do you think the arrow coming from nowhere is? This thing over here. So yeah, go ahead.
I assume it's input.
It's input in some sense. So when you turn on your computer and you start running a program, there must be some entry point into that program, right? It has to start somewhere. So like a main function, for example, there's always exactly one way to enter the program. So that arrow coming in is an indicator what state is the quote-unquote start state. So the arrow that comes from nowhere tells you where you're going to start in the machine. So in this case, what is the start state of this machine? Q0, right, because that's the state that it's pointing to. And I actually have no idea why they're called Q and not called S for state, but yeah, it's just a notation that everyone's unfortunately gotten used to. Okay, so let's talk about this double circle on the right. So a double circle means that the state is a 1 state. So remember, we attached a 0 or a 1 to each of the states, and Q1 in this case is a 1 state. We'll have another name for this, for what a 1 state is, but I hope it's actually clear. 1 means that we say yes on the input, and when we don't have a double circle, that means we say 0 or no on that input, whatever the input was. Any questions on that? So let's actually do an example. I'll talk about the arrows going between the states in a second. So let's actually consider one input of this machine. Well, the arrows going between, those are what are called transitions of the machine. So remember, each instruction goes from a state of the machine to another state of the machine, maybe the same one, but it goes from a state to a state of the machine. So these arrows going between the states, those are the transitions. So this tells us that if we have a state Q0, if we're in that state right now, at the start or at some later point, and we see a 0 on the input string, then what's going to happen is we're going to consume that character of the input. We're going to eat it like Pac-Man. Then we're going to transition over to the Q1 state. Okay, so what's happening is we have this input string here. Then we're going to consume the string character by character all the way through the string and then change the state as we need to. So let's actually do an example. So let's have the input 0, 0, 0. So 3 zeros here. So when I turn this machine on, before I've read anything of the input string, what state of the machine am I in when I first turn it on? Q0, good. So we're in Q0 right at the very start of the machine. So I put Q0 here before the vertical line to indicate that this is the state we're starting in, and then we'll change the state as we go. So we're in Q0 right now, and we see, what do we see on the input now? What character do we see on the input? Just a 0, right. So if we see a 0 on the input, then that means we got to execute the transition labeled 0 coming out of Q0. So it comes out of Q0 and goes to what state? Q1. So the current state right now is Q1. Good. Am I going too fast? Or do I need to speed up or slow down or do exactly the same? Okay. So now our current state is Q1. What do we see on the input? Well, we have consumed that character 0 at the beginning. We'll never see that 0 again, crucially. We'll never see that particular 0 again. But do we see another character on the input? Yeah, I'm being pedantic for a reason because getting the fundamentals for this is really important. So we see a 0 on the input, and our current state is Q1. What state am I going to go to next? Q0. Good. And after going to Q0, then we've consumed that second 0. Cool. Are we done with the computation? So I'll tell you that we're done with the computation when we have read the entire input string. Once we read the input string, there's no way to revisit anything of the string anymore. So we're done with the computation. Are we done at this point? No, there's 1 0 left. So what state am I going to go to? Q1. Good. And then I've consumed that character. That character's done. There's no more input anymore. So that means we're done with the computation. What state did we end up in? Q1. Is that a 1 state or a 0 state? It's a 1 state because it has a double circle on it. Cool. So for the input 0, 0, 0, what are we going to say? Are we going to say a 0 or are we going to say a 1? We're going to say a 1. So here we're going to say 1 or yes. So, and then the term that we're actually going to use, and I'll introduce it later, is except. So this 2-state machine accepts the input 0, 0, 0. What other input does this machine accept? Just as an example.
0, 1, 1.
Well, there's no transition labeled 1 on it. So the only thing that the string can have is zeros.
So 0, 0, 0, 0, 0.
Right. So 5 zeros. What are some other ones?
As many zeros as you want.
Any number of zeros?
Except for odd numbers.
It would have to be every odd number.
You have to be an odd number of zeros. So what is the set of strings that this machine says yes or accept on? Well, it's all zeros that have an odd length. Nice. So this machine accepts exactly the strings with an odd number of zeros. and it doesn't accept any other one. And why is that? Because if you have an even number of zeros in your string, then you're going to be at Q0. And you can prove that via induction or something. So if you have 0 zeros, then you're going to be in Q0. And if you have some even number of zeros, then inductively you're in Q0. Then if you add 2 more, you're going to go back to Q0. So it accepts exactly the strings that have odd length, which are all zeros. Pretty cool. Any questions about this? So this machine, we didn't need anything complicated. We don't need main memory or anything. We don't need a giant storage or to hold additional parts of our program or anything. We can just have a simple 2-state machine that solves the problem of whether the length of the string is odd or even, if we wanted to convert this to even. If I did want to make a similar machine, which instead of being odd strings is even length strings instead, what would I have to do?
You just switch which side the accept.
Right, yeah. So I would just say for the even one, I would make Q0 the accept state or the 1 state, and Q1 be the not accept state, whatever that means. Okay, so I would just swap the role of Q0 and Q1. Another thing I could do is I move the start state indicator over to the Q1 state. That'd be another thing I could do. Okay, any questions about this? Let's see, so let's try to do one more. So this one's a little bit more complicated. It's going to have 4 states this time. And instead of being just zeros on the input, it's going to have zeros and 1s on the input. So then, let's see. So the 0 transitions are going to go back and forth. So between 0 and 1 and 2 and 3. And the 1 transitions are going to go up and down. The outside 2. So Q0 has zeros going back and forth between Q0 and Q1, between 2 and 3, and then 1s between 0 and 2 and 1 and 3. So a little bit more complicated, but still only 4 states. So what's an example of a string in this machine that is accepted or says 1 on? Any example?
0.
Yeah, just 0. The 0 works, or 1 works. Yep. So if we just make a list of strings, 0, 1 work. What about other strings?
0, 1, 0.
Yeah, 0, 1, 0. And then there's other ones. Any ones of length 2? No. And how can you tell? Because if you have an even number of characters that you've read so far, you're going to be either in 0 or 3, Q0 or Q3. And if you have an odd number, you must be at one of the other 2 states, which are Q1 and Q2. So can you describe in English what the strings that are accepted by this machine is?
Any strings of an odd length that alternate from either 0, 1 or 1, 0?
It doesn't have to alternate. So could I accept 0, 0, 0 on this machine? Yeah, because you would go 0, 1, 0, 1. So it's in fact all binary strings of odd length. So it's actually very similar to the example that we did already. So we're actually out of time, but I'm going to ask you to think about this question. So we have a machine with 4 states for all binary strings of odd length. Can you make a machine that's smaller that does the same task? So I want to have a machine that accepts all binary strings of odd length, but can you do it in fewer states than 4? So then for that reason, I'll see you at lab later today.